Hey, hello everyone. So my name is Michał. I work for Curity, and at Curity we work on our own authorization server. So we deal a lot with topics around authentication, authorization, securing KPIs, and obviously Auth and OpenID Connect. And when you think about securing KPIs, you usually think about the access token, verifying the access token, making sure that the request is properly authorized. But in fact, a very important part of security is to make sure that the access token is secure on the client side. Because if at the client side somebody manages to steal the token, they will be able to access your API with a legitimate token. And that is a serious problem. And that's why I want to talk today about securing SPAs and making sure that SPAs handle access tokens in a good way. And for that, we'll be using the token handler pattern. So let's start with how it works today. When you have an SPA and you use Auth or OpenID Connect to authorize access to your APIs, so usually you would have something like a web host or a CDN from where you serve your static content, so all your JavaScript, CSS files, and they end up in the browser starts the SPA, and whenever the user needs to access some secure content, the SPA will redirect the user or open an iframe that will redirect the user to the authorization server, start the OIDC flow, and the authorization server will authenticate the user, and eventually, at the end of the flow, the SPA will get an access token, and then it can use the access token to call your APIs and get some data that belongs to the user. This approach has some benefits. It gives us that productive development, mainly because thanks to that separation of concerns. So on the front end, we can concentrate on creating the views, the components, to make sure that everything in the browser works and is displayed in a correct way. And all the static files can be deployed, for example, to a CDN. They don't have to be deployed in the same way as your APIs. And your APIs are secured, the access to the APIs is properly secured, and also the authorization server is in control of authenticating the user. So this gives us that nice separation and nice options for both development and deploying the whole solution. But this approach has some problems. The first problem, and in my opinion the more important one, is that storing tokens in the browser is not secure. The SPA, when the SPA gets a token and subsequently calls APIs, it needs to store the token somewhere. It can store it in the memory, or it can store it somewhere like a local storage or session storage, so that when the user comes back to your SPA, the user doesn't have to log in again, but can use the token to call your APIs. But when a token is accessible by JavaScript, it's prone to XSS attacks. And unfortunately, there's nothing we can do about it. Any token that you have in your browser and is accessible by JavaScript is prone to an XSS attack, and someone can steal the token and legitimately call your APIs. And there's also another problem with this architecture, with this approach that I showed you, that very often your SPA will work on a different domain than your authorization server. And as we know, browsers are now dropping support for third-party cookies. And so that means that solutions like using something called a silent refresh. So in an iframe, you want to refresh the access token of the user, make sure that the user still has an active session with the authorization server. That will not be possible soon, because this uses third-party cookies when the authorization server uses a different domain than your SPA. So this is also a problem for the SPA. Current solution proposed by the Auth community is to use a backend for frontend. It's described in a BCP paper that is named Auth2 for browser-based apps, and there the Auth community recommends that you shouldn't keep tokens in the browser at all because it's not possible to secure them there. You should instead use add a component, a backend component that would handle the tokens, and then that component will use cookies to communicate with the SPA. Cookies are currently deemed more secure, also because a few years ago browsers introduced that new property of cookies, the same site, so we can better protect cookies against CSRF attacks, because previously that was one of the main concerns with cookies, that it's quite easily to perform a CSRF attack when you have a cookie-based session. Still, that document, that BCP, it doesn't show you how to implement that BFF, what is the API, what is the architecture of that, and so the question is how to do it in a way that will allow us to maintain all the benefits of the SPA architecture that we mentioned before. And at Curity, we thought about this problem, and we created something we called the token handler pattern, which is sort of an implementation of the BFF mentioned in the BCP. We decided to not to call it BFF because we think it's a bit an overloaded term. It's used in quite a few different contexts. So we called it token handler pattern, and basically what it gives you is that component that will handle your tokens and use cookies to communicate with the SPA. We described the pattern. We described what we think, how we think you should deploy it and integrate in your infrastructure, and what API your SPA could use to communicate with these components. We also created a few open source implementations of the token handler, both the auth agent and auth proxy. I'll describe them in a second. There's a Node.js implementation, a Kotlin implementation, and we created some POCs for some common API gateways. We decided to actually divide that component, that BFF component, into two components. So there's a component that we called an auth agent and another one that we called auth proxy, and I will describe them, what they do in a second. When we were thinking about this approach, we wanted it to retain some properties of the architecture that I mentioned before. So we wanted to still have that separation of concerns, that the SPA code, that static files can be served from an unsecured web host, from a CDN, or what have you, and cookie issuing is a concern of a different component. It's not connected to your static host, so nothing changes from that deployment point of view. We also thought that having those two components is a better approach because when an SPA calls your API, it usually does that through an API gateway, and it usually does that very often, and it's a request that you want to happen quickly, and we thought that adding another component in front of your API gateway might become a problem for your performance. So the auth proxy, we think it's best to implement it as a plugin for your API gateway. And we also wanted to create the API in such a way that the SPA still remains in full control of what happens with the login flow, so that the user isn't redirected suddenly somewhere, but the SPA has full control over when to redirect the user to the authorization server. So the first component, the auth agent, that's sort of a wrapper on your auth and OpenID Connect flows. This agent exposes a few different endpoints that you can use to perform the OIDC flows. I won't describe all of them here, but the most important ones are the first two, login start and login end. And so how the flow looks like with auth agent. The SPA, when the SPA wants to log the user in, it will first call the auth agent at the login start endpoint, and it will get back an authorization URL. The authorization URL is the auth URL that you normally use to start an auth or OIDC flow. But as I said, the auth agent doesn't redirect the user. The SPA gets the URL back, and it can, for example, save the state of the application, save what the user is currently doing, and then redirect the user to the authorization server. Authorization server performs login as usual, and as part of the auth code flow, at some point it will return the authorization code back to the SPA, and now the SPA calls the auth agent again, now on the end endpoint, and the auth agent is responsible for exchanging that code for a set of tokens, and it takes these tokens, encrypts them, and puts them in cookies, and sends the cookies back to SPA. So now the token isn't in the browser, but SPA uses cookies. In order for that solution to be secure, the cookies need to have some concrete parameters, and one of them is HTTP only, so that obviously JavaScript cannot read content of these cookies. That's, I think, the most important one for that solution to make sense. Now only the browser has access to that cookie with the access token and not JavaScript. We also use the same site strict flag so that it's harder to perform a CSRF attack, and the secure flag so that the cookie isn't sent over unsecured network, only via encrypted connections. And you can also use the domain and path attribute to further limit where those cookies are sent to. So, for example, you make sure that the cookies are only sent to your API domain where actually the API used them, and not, for example, to your static web host domain. Or, for example, when you have the refresh token, we put it in a separate cookie, and that cookie can be used only on the refresh path of the auth agent, so that it's only sent when the SPA actually wants to refresh access tokens, and not to every call to your API. And the value is encrypted. Here is an example of how such an access token cookie looks like. We encrypt the value so that even if someone manages to steal the cookie, they will not be able to read the actual token value because they would need the decryption key. If you use opaque access tokens, then cookie values end up quite short, and that's not a problem. If you use JOTs for your access tokens, then you might sometimes hit some limits of browsers because the resulting encrypted cookie will be quite long, especially if you put a lot of data in your JOTs. So we recommend that you use opaque tokens as access tokens and refresh tokens. And because the token is put directly into the cookie, then the token handler component is actually stateless, so it doesn't have to save anything anywhere. You have all the information in that cookie, and the token can be decrypted and taken from the cookie. And that is actually what happens in the second component, so the auth proxy. So this one sits in front of your API. And again, we thought that it's good to have that as a separate component and not implement it as a separate service, but as a plugin for your API gateway. I think currently all or most APIs have API gateways in front of them, and it's quite easy. For most of them, it's quite easy to extend their functionality. So, for example, in Kong or in Nginx, you can create a Lua plugin, and we created actually an open source version also of such a Lua plugin. You can put that in your API gateway, and what that auth proxy does is it reads these cookies, decrypts the values, and puts the actual token value in the authorization header and sends the request to your API. So the API still works as before with tokens in authorization headers and doesn't have to deal with cookies. So the API doesn't know anything about the change in the architecture. The APIs actually, it's best for the APIs to work with JOT. So we also recommend when you use opaque tokens that the proxy also performs introspection of the token and exchanges the token for a JOT and then sends the JOT to the API. As a result, you end up with an SPA that has a security level of a website, of a plain old website that used cookies for sessions. It gives much better protection against XSS attacks. It still has some vulnerabilities against CSRF, but there are some techniques to try to prevent that. It's still also vulnerable to some XSS attacks. For example, if someone manages to attack your SPA, they will be able to send requests from that SPA to your API, and the browser will just add the cookies, and the attacker will be able to read your APIs. But now the attack is limited only to the user session. If the user closes the browser, closes your SPA, the attacker won't be able to continue with the attack, to continue with reading your APIs. What is more, the attacker won't be able to steal the token, send it to their server, and continue the attack offline from there. So the surface of the attack is very much limited. Also, that separation, again, the separation of concerns gives us possibilities to implement some additional or different approaches to auth flows without changing anything on the SPA side or the API side. For example, if you wanted to use some financial grade solutions like push authorization requests, that is a more secure way of starting an authorization request in auth. It can be implemented directly in the OAuth agent, and the SPA don't have to know anything about it. It will still just call the start endpoint and the end endpoint, and it will now benefit from a better security without any change on the front end. So I wanted to quickly show how it works. So we have a project where you can deploy all the components that are needed for the token handler, and there is a simple script that will deploy the different Dockers, containers. So if you look here, there's a bunch of containers deployed with the project, and the most important ones is that there is a separate component now, an OAuth agent that will sit in front between your API, between your SPA and the authorization server, and we use the Kong API gateway for the API, and there's a web host that will serve some static files and some business API, some simple API that is protected with the access token, and we use Curity as the authorization server. But you can use any authorization server that uses standard auth or OpenID, because that's the solution is based on standards. So what I get as a result is a simple SPA. It's visible, right? In the network tab, when I sign in, you will see the call to the start endpoint, and is that the post? It is. Oh yeah, because that one doesn't have. Oh, why no headers? Okay, let's try to log in then. I don't know why the start endpoint didn't show anything, but when calling the end endpoint, you'll see that it returns a bunch of cookies with some encrypted values. I don't know if that's visible from far, but the user is now logged in, and you can call APIs with So when you look at the request, we don't have the usual, in the request headers, we don't use the usual authorization header. The request only uses cookies, sends cookies to an API, and still the API responds with a successful response. The API accepts only JOTs in the authorization header. It doesn't know anything about the cookie that's being used in the request. So the solution also works in multiple browser tabs because these are cookies that are on your domain. So you don't have to think about whether the user will open a new tab and whether they will be logged in or not. It's just cookies in the browser, so that works. And if you sign out, the user will be signed out also from all tabs because the tabs don't have the cookie anymore. So the key takeaway here is that that pattern is thought for projects, for SPAs that use auth and OpenID Connect. If you have SPAs protected with some other standards, you still can use the pattern. You just won't be able to use the implementations that we provide because these are provided for auth and OpenID Connect. But you can use the pattern of a BFF that handles cookies instead of having tokens in your SPA. You can think of that project as as a profile, as an implementation profile for the BFF that is recommended by the best current practice for auth for browser-based apps. Where in the pattern we propose an architecture and an API that you can use in your projects. And we also created those open source components and those POCs for a few different common API gateways. So, for example, we created some Lambda functions for Cloudflare gateway, or configuration for Microsoft Azure that you can use to implement this pattern easily. And if you want to read more, there are articles on our website about the whole pattern and how it works. There's also a white paper with some more detailed information about the security issues of websites, of SPAs, the BFF pattern, how it all works together. And you can also have a look at the code example that I showed you here. There are also links to the implementations of the token handler, and you can just download the code, start it yourself, and have a look how it works. And that's everything from me. If you have any questions.
First, big thank you, please, to Michał. Yeah. Okay, any questions? I'm sure there are security issues abounding, increasing in security issues. At least that's what I've been told, that people are really concerned, even more today than ever. Any questions for Michał?
So I was wondering, what is like a good YAR way, for example, if I have like two browsing contexts, two tabs open, and I want to log out from one tab, and I remove the cookie, so I'm not authorized anymore. And how can you, for example, share the state to the other tab to say them that you're logged out?
Yeah, so here we, for example, in this example, we use what is called it's in OIDC. There's a logout that is initiated by the authorization server. So the client will listen to events from an authorization server and can inform the SPA that the user has logged out, and so that you have to refresh. So I can show you that afterwards. That in this code that we have, the SPA, when I logged out from one tab, I was already logged out on the other tab without refreshing anything.
Mm-hmm. Thank you.
Once more, thank you to Michał for that speech.
Thanks.